In the last video, we learned some shortcuts for taking derivatives that are going to be really useful once we kind of get the hang of how to use them. I want to recap those shortcuts in this video because they're so important, fill in a couple of gaps, and then just do a whole bunch of examples to get you really comfortable with these rules. So the big takeaways from the last video were 3 different derivative facts. The first one, that is often referred to as the power rule, tells us that the derivative of x to the n power for any n is just n times x to the n minus 1. Think the derivative of x to the 6th is 6x to the 5th. The second one, which we might refer to as the coefficient rule, tells us that you can essentially ignore coefficients for the purpose of taking derivatives. So instead of asking you the derivative of x to the 6th power, if somebody asked you the derivative of 10x to the 6th power, all you would have to do is figure out the derivative of x to the 6th power, which is that 6x to the 5th, and then multiply that by 10 to get 60x to the 5th power. And then the third rule, which maybe we refer to as the sum and difference rule or just the sum rule, whatever, is not written here. That's kind of funny. It says that the derivative of the sum of 2 different functions is equal to the derivative of the first function plus the derivative of the second function. If you're the type that really likes formulas, here is a summary of what we went over in the last video. Most students prefer to not just memorize these formulas, but instead kind of understand what's going on. So I think the easiest way to understand what's going on is kind of talk about the process in which you'd use these different rules. So for this first one, rather than memorizing that the derivative of x to the n is nx to the n minus 1, it might help to think I'm going to take the old exponent and I'm going to kind of bring it down in front. And then the new exponent is going to be 1 less than the old exponent. So when I take the derivative of x to the 10th power, I'm going to take that old exponent and bring it down in front. And then the new exponent is going to be 1 less than that old exponent, giving me 10x to the 9th. The second rule, you might remember by thinking I'm just going to pull constant multiples out in front. So when you ask me what's the derivative of 5x to the 10th power, I'm not going to worry about the derivative of 5x to the 10th power. I'm just going to think about the derivative of x to the 10th power. I'm going to take that constant multiple and pull it out in front of my derivative. Then just apply the power rule. The derivative of x to the 10, I bring the 10 down in front, subtract 1 from the exponent, I get 5 times 10x to the 9th, or 50x to the 9th power. Finally, the last rule, which I must have copied and pasted from above because it's written incorrectly here as well, says that the derivative of a sum of 2 functions, f of x plus g of x, is the derivative of the first function, f of x, plus the derivative of the second function, g of x. The derivative of a sum is just the sum of the derivatives. You're taking the derivative of x cubed plus 4x squared, no problem. Just take the derivative of x cubed and then add to that the derivative of 4x squared. Take this one big, difficult, maybe, problem and break it up into 2 simpler problems. The derivative of x cubed, just using the power rule, is 3x squared. And then the derivative of 4x squared, you could probably do it all in one step, but I'm going to do it in 2 steps to really show my process. I'm going to first use the coefficient rule and take that 4 out in front, but then I still have to take the derivative of x squared. Fortunately, I know the derivative of x squared. Using the power rule, it's 2x to the first power, or just 2x. So my answer is 3x squared plus 4 times 2x, which I can simplify to get 3x squared plus 8x. The derivative of this sum is just the sum of these 2 different derivatives. A couple more things to fill in that don't technically fit any of our rules. The first one is that if you just have x, in other words, x to the first power, its derivative is just the number 1. The derivative of your variable is just 1. This makes sense for all sorts of reasons. Maybe the easiest way to show you this is just sort of a graphical approach. If you think about the function f of x equals x, that's a linear function with y-intercept of 0 and slope of 1. It's this diagonal line right here. You take any point on this function and consider the slope of the tangent line to the curve. The slope, because this is a straight line, is just going to be 1. So it makes sense that the derivative of x is just 1. Another way to think about it is you can almost use the power rule. This x really means x to the first power, so you can bring that 1 down in front and you get 1 times x to the 0 power. And maybe you learned in a different class that anything raised up to the 0 power is just equal to 1, which is almost true. So you get 1 times 1, which just gives you the 1. I guess you can kind of think about the power rule for this fact, but it might be more useful to just memorize that the derivative of the variable, if the variable is just by itself, is just the number 1. And another thing that I can prove to you graphically, and you can almost use the power rule for, is that the derivative of a constant is just 0. If you think about the graph of, I don't know, g of x equals 3, it's just a horizontal line whose height is 3. It's y equals mx plus b, where m is 0 and b is 3. Now think about the slope of the tangent line to this curve at any point. Pick whatever point you want. If you're drawing a tangent line, it's just a horizontal line. It's got a slope of 0. That's why the derivative of a constant is just 0. Please be careful here. This is talking about a constant all by itself. So this is talking about why this plus 1 went away and didn't show up in the derivative. It's not talking about a coefficient like -4, which is a constant times some function like x, or a constant like 1/4 that's serving as a coefficient being multiplied by this function x cubed. We do not use this rule on this 4, for example. We use the coefficient rule to bring this 4 out in front of the derivative. You never take the derivative of 4. If you ever wrote d over dx 4, that would be equal to 0. But you don't do that because of the coefficient rule. You bring it out in front of the derivative so you don't have to take the derivative of it. I think some examples will make that much more clear. Here's a polynomial. It would be awesome if you could figure out the derivative of this polynomial. And feel free to pause and do it on your own if you want. If you're really following this, you could probably figure this out without showing any work at all. But I'd encourage you to show all of your steps if you can to really help you understand the different rules. Because while you might not need them right now, later on when things get more complicated, it'll really help to have all the different steps shown. So if I were trying to write this up in as much detail as possible, what I would first do is use the third rule that we learned, this sum rule, that says if you're taking the derivative of a sum of 3 different things, which is what we have here, 10x to the 5th plus negative 6x cubed plus 25. All you have to do is take the derivative of each of those things individually. Take this one hard problem and break it up into 3 easier problems. Then work on each of those problems individually. Might as well go left to right. For this first one, all we're trying to do is figure out the derivative of 10x to the 5th. Don't worry about any of this stuff. It's just the derivative of what's inside these parentheses. How would you figure that out? Well, you'd notice that you have a coefficient, the number 10, and so you could bring that down in front of the derivative, and we'd still have to figure out the derivative of x to the 5th power. We've still got work to do on all these guys, but maybe it'll make the most sense to finish up this one. In the next step here, I would use the power rule. I'd say the derivative of x to the 5th power is 5x to the 4th power, and 10 times 5x to the 4th power is 50x to the 4th power. Now maybe I can move on to the second term. I want to take the derivative of negative 6x cubed. The way I do that is I bring the negative 6 down in front, and then I still have to take the derivative of x to the 3rd power. Note this looks kind of weird with the plus minus thing going on right here. Instead of adding a negative number, it might make more sense to just think about this as we're subtracting 6 times the derivative of x cubed. And the derivative of x cubed is 3x squared using the power rule. If you don't want to run into this kind of strange case where you have the plus and the minus written right next to each other, what you could have done in this first step up here is made this the derivative of 10x to the 5th. And then instead of plus negative 6x cubed, you could have made it minus the derivative of positive 6x cubed. Really what we're doing is we're combining the coefficient rule and the sum rule here to make kind of a new sum and difference rule. But rather than worry about all the minutia, you can kind of see that things are just going to work out the same. It doesn't matter if I take the negative out at this stage or if I wait to take the negative out at this stage. So feel free to, instead doing the green method, do the blue method. But I'm going to continue with the green method just because I think that's the one that lines up with the rules that we learn the most. So for any students who are struggling with this the first time through, I want this to be as predictable as possible. Anyways, negative 6 times 3x squared is negative 18x squared. So all that's left is for me to take the derivative of 25. Well, 25 is just a constant, and we learned that the derivative of any constant is just equal to 0, so I just have a plus 0 right here. If you want to carry that plus 0 to the next line, you can, but you really don't have to. The final answer is just going to be 50x to the 4th minus 18x squared. I've got a lot of examples, but some of these get a little bit complicated. So I think what I'm going to do is do one more example in this video and then save the more complicated examples for the next video. So last example of this section, the derivative of 4x to the 10th minus 6x to the 9th plus 2x squared minus x over 2, that's a little tricky, plus 3/5. You can try this on your own if you want, but if you want one little hint before you do so, recognize that negative x divided by 2 is the exact same as negative 1/2 times x. What you'll see as a big challenge in calculus is rewriting expressions to get them into a form that's conducive to using one of your rules on them. Negative x divided by 2 might not be conducive to any of the rules we've learned, but negative 1/2 times x certainly is. So how would you take this derivative? Well, it's a little overwhelming, but first just recognize you have these 5 different terms. So when you're taking the derivative of a sum and difference of terms, all you gotta do is take the derivative of each term individually. So eventually I'll have to figure out the derivative of 4x to the 10th, and then I'm gonna subtract the derivative of 6x to the 9th. Note that you could have also written plus the derivative of negative 6x to the 9th. And then I'm gonna add the derivative of 2x squared. And then I'm gonna subtract the derivative of 1/2 x. Again, negative x over 2 is the same as negative 1/2 x. So I bring the negative out and then take the derivative of 1/2 x. And then finally, I'm going to add the derivative of 3/5. You might be at the point where you can do this in a single step. You can just look at this and tell that the answer is 40x to the 9th. And if you're there, that's fantastic. I'm going to eventually get to that stage. But for now, I'm going to keep breaking these up into the different steps. I take the 4 out in front using my coefficient rule. So it'll be 4 times the derivative of x to the 10th power. And the derivative of x to the 10th is 10x to the 9th using the power rule. So I have 4 times 10x to the 9th, or 40x to the 9th power. I'm done with this first term. I move on to the second term. I'm subtracting the derivative of 6x to the 9th power. I can bring the 6 out in front and multiply that by the derivative of x to the 9th power. Bring the 9 down, so I get negative 6 times 9x to the 8th power. And since negative 6 times 9 is negative 54, I get negative 54x to the 8th power. My next term, I got the derivative of 2x squared. I'll take 2 times the derivative of x squared. The derivative of x squared is just 2x, so I got 2 times 2x, in other words, 4x. Next, I want to subtract the derivative of 1/2 x. I'm going to take the 1/2 out in front, and I'm going to multiply that by the derivative of x. But remember that the derivative of a variable is just the number 1. So I have negative 1/2 times 1, in other words, negative 1/2. And then finally, the derivative of 3/5. You might think you have to rewrite this as like 3 times 1/5 or something, but you don't. 3/5 is just a constant. It's just a number. Anytime you're taking the derivative of a number all by itself, the answer is just 0. So my final answer for the derivative of 4x to the 10th minus 6x to the 9th plus 2x squared minus x over 2 plus 3/5 is just 40x to the 9th minus 54x to the 8th plus 4x minus 1/2. 2 comments. I bet you can go straight from here all the way to here. And that'll be way more efficient, and eventually you'll want to get there. But don't do that until you're positive you can get it right every time, until you really understand these different rules. Because you want to be an expert with these rules, not for examples like this, but for examples when this becomes much more challenging functions to really understand what you're doing. So don't skip these in-between steps until you're really, really good with them. And I think that's all the comments that I want to make for this video. I'm going to stop this here, and in the next video, we'll work through the rest of these examples, which are a little bit more challenging.